This is slide number 23 and I am your presenter Asloob Mudassar. In the previous slide we have presented the cosine function and its Fourier transform, and you know that there the Fourier transform existed three delta functions which we have shown in the diagram on the right. This is actually the Fourier plane, and the center this indicates three delta functions. And on the left we describe these delta functions as delta of fx and fy is a point source in the Fourier plane at the location at the center of the Fourier plane where the coordinates were fx is equal to 0, fy is equal to 0. The next on the right one is actually delta of fx minus f comma fy is a point source at the Fourier plane located at the coordinates fx is equal to f comma fy is equal to 0. The point on the left is a point source on the left that is represented by the delta of fx plus f comma fy is a point source in the Fourier plane at fx is equal to minus f and fy is equal to 0. So these are the three delta functions. The two-sided delta functions which is have an amplitude which is half the amplitude of the central point source. Now let's see that the cosine function, that is O3 function, was 1 plus cos of 2 pi f into x, and we can write the cosine function in terms of its exponential form, which is 1 plus half e to the power iota 2 pi fx plus half into e to the power minus iota 2 pi fx. So let's analyze that what angles that these sources, that is the source on the right hand side and the source on the left hand side, what are the angles that these sources make with the x-axis. In order to calculate that one, we analyze the first exponential in the cosine function, so that is half into 1 into e to the power iota 2 pi fx. So that is you see that we can write 2 pi over lambda, and then we can multiply it with lambda, so that we can introduce the wave number k. So we have half into e to the power iota kx into f lambda. So we can replace f lambda with the cos alpha, and we have final expression as of half e to the power iota kx into cos of alpha, and there we can define the alpha as a cos inverse of f lambda. So this you saw that this is what one of the point source makes an angle alpha with the x-axis. The statement below is that the propagation vector makes an angle alpha with positive x-axis and lies in the xz plane. So let's analyze the second exponential in the cosine function, that is equal to half into e to the power minus iota 2 pi into fx. So again we are writing it in the form of the propagation vector k, and at the end we have half into e to the power iota k, within the bracket we have a minus x multiplied by cos of alpha prime. So here we can write that alpha prime is equal to cos inverse f lambda. The propagation vector makes an angle alpha prime with the minus x axis and lies in the minus xy and lies in the minus xz plane. So you see that we have shown that the angles that these spots, that these point sources, the central point source makes no angle because it is along the z axis, whereas the point source on the right and the point source on the left respectively makes angle alpha is equal to cos inverse f lambda, but one with positive x direction, the other one is with negative x direction. Okay, next we want to write down the relationship between the spatial frequencies contained in an object and its Fourier frequencies. Consider an object having patches of different fixed spatial frequencies oriented along the x-axis or along the y-axis. You can see in this figure that we have 4 patches in one row. One of the patch is oriented along the y direction, the other one is along the x direction, and the other 2 patches are along the 2 diagonal directions. And we have in the first row the frequency is the spatial frequency is the lowest. In the second row the spatial frequency is slightly higher. In the third row the spatial frequency is relatively more higher, and in the last row this contains the maximum spatial frequencies of the contained in the object. So we have these 4 rows, or actually these are actually the the 16 objects. So let's read about these objects. Spatial frequencies are actually the number of line pairs per millimeter, that is the black line and the white line together form a line pair. So how many line pairs are there in per millimeter, or the line pairs per inch contained in an object? This will be regarded as the spatial frequency. Generally, an object contains a range of spatial frequencies. Some spatial objects may contain a single spatial frequency, and some may contain a certain range of spatial frequencies. We shall be analyzing these spatial frequencies in greater detail in the next few slides. But you can see that in each of these we have one spatial frequency. For example, in the first row we have a single frequency, in the second row we have a single frequency, but that frequency is higher than the previous one, and in the third row we have again the single spatial frequency higher than the previous one, and in the fourth row we have again the single spatial frequency but higher than the previous one. So this is the end of slide number 23.